Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 2 of 2 on the topic of multiple linear regression, and we'll discuss additional considerations for multiple linear regression models. Let's get started. The coefficient of determination gives us the percentage of the variability in the response variable that's predicted by our model. Remember that the SSE is our objective function, and we want that to be as small as possible. SST is the total sum of squares, which is in essence the variance of the response variable. As the SSE approaches 0, r squared approaches 1. SSE equals SST if the regression line is y equal to the mean of the response variable. Then the r squared is 0. We use adjusted r squared to compare models of varying complexity. The adjustment factor reduces adjusted r squared with each additional parameter that's added. This means that the gain in regular r squared has to be bigger than the penalty for adding a parameter in order for adjusted r squared to go up. These two metrics are equal in the case k equals 0, which is an intercept-only model. However, we just saw that for an intercept-only model, the r squared is 0. This means that the adjusted r squared is always less than the r squared unless r squared is 0. Multicollinearity is a problem that arises in models with multiple predictors which are linearly related. If one predictor is a linear transformation of another, for example if two predictors are the same variable but measured in different unit systems, then they're collinear. Another way that multicollinearity can occur is if multiple columns always add up to the same value, for example percentages adding up to 100%. Multicollinearity can cause serious difficulties in fitting the model. The matrix math we saw previously can completely fall apart with highly collinear predictors, resulting in a complete failure to estimate the parameters or with very unreliable estimates. You can wind up with all kinds of unexpected results, such as the wrong sign for the model coefficients. Almost always, the model fit has large standard errors, resulting in a high p-value for the coefficients. This can happen even though the entire model, using the f-test, is significantly better than an intercept-only model. This can be the most significant problem facing multiple linear models. It's definitely good practice to check if your predictors are multicollinear. The remedy, if you have identified one or more predictors that are multicollinear, is to remove the worst offenders from the model until the multicollinearity subsides. One way to test if your predictors are multicollinear is to compute the correlation between each pair of predictors. Sometimes this can detect if variables are multicollinear, but it can occasionally fail. Multicollinearity will be presented by large positive or negative correlation between the predictor variables. A more reliable predictor of multicollinearity is the variance inflation factor. The VIF for a predictor is computed using this formula, where the r squared j comes from computing the regression model between the predictor you are testing and the remaining k-1 predictors in the model, and extracting the model r squared value. If the model r squared is small, the VIF approaches 1. As the r squared gets larger, VIF approaches infinity. Most statistical software packages can compute the VIF for each predictor for you. In R, you can compute them using the VIF function out of the companion to applied regression library. Generally, VIF values greater than 5 require a closer look, and greater than 10 are problematic and require treatment. Usually the treatment is to remove the highly collinear predictor variable from the model. Transformations can be very important in linearizing your model in the multivariate case. By using transformations on your predictor variables and your response variable, you may be able to improve the model fit and better meet the linearity assumption. The figure on the lower right shows the general shape of the scatter points and then a list of various transformations on x and y that you might try depending on the shape of the scatter. The most commonly applied one by far is the logarithm, which takes data spread across orders of magnitude and linearizes them. The reciprocal and negative reciprocal have the opposite effect, taking data spread over a small range and expanding it. Finally, polynomial powers such as squaring or cubing are commonly used as well. Sometimes there's a good theoretical basis for the relationship between two variables that take the form of a polynomial. To fit this as a linear model, each polynomial term is treated as a separate predictor, so x, x squared, x cubed, etc. are each a predictor that get a coefficient. There are typically two problems that occur with polynomial regression. The first is that powers of x tend to be correlated, which can lead to multicollinearity issues. The second is that high powers of x tend to create a very wide range of magnitudes, which can result in coefficients with very different orders of magnitude. Both of these problems tend to lead to numerical errors in the least squares procedure. Aside from the fitting issues that occur, extreme caution should be taken with polynomial models as their fits can be exceptionally unreliable outside the range of data. High-order polynomial models tend to be overfit to the data, meaning they will perform well within the range of the predictor data, but fail, sometimes spectacularly, outside the data. If you use polynomial regression, consider centering the x variable, that is, subtracting off the mean of x, which can help reduce multicollinearity. Just remember that for predictions with the model, that you also have to subtract off the original sample mean you used in your model fit in order for the coefficient to be appropriate. Generally, it's best to limit the powers you use to a cubic model if you can. This prevents excessive overfit and avoids problems where the fitted curve has very different behavior outside of the data than inside of it. Cubic curves only have one inflection point and either has two critical points or is monotonic. However, in the situations where the theory justifies going to higher powers, a quartic or quintic may be used, but there need to be enough data to support that decision, and extra care should be used. It's best to never exceed a fifth-degree polynomial. We just mentioned centering the variables, which is a technique that can reduce multicollinearity, and here we take it one step further after centering it by scaling it. This results in standardized variables. Standardization is the same as computing a z-score. You subtract the sample mean from each value and then divide by the sample standard deviation. This puts the predictors and response variable all on the same scale, centered at 0. This also reduces the magnitude of polynomial terms, which can grow in orders of magnitude with higher exponents. Standardization should be used on both the response variable and all the predictors. There are two effects of standardizing the variables. First, because all of the involved variables are centered at 0, the constant or intercept term is eliminated from the model. This actually has the side effect that estimation of the remaining coefficients in the model is simpler and numerically more stable. Second, with all the variables on the same scale, the magnitude of the effect of each predictor can be directly compared by looking at the coefficients. A larger coefficient indicates a larger magnitude effect on the response variable. Continuous interaction is a somewhat difficult topic, but we'll cover a brief overview of it here. Interaction occurs when two variables interact to create a bigger or smaller response when their values are larger. In other words, the effect of x1 on y is not the same depending on the value of x2. In the model shown here, the effect of a 1-unit increase of x1 when x2 is held constant is beta 1 plus beta 3 times x2. If beta 3 is positive, this means that the impact of x1 is greater when x2 is larger. This means that the two variables interact to characterize the response. You can always try to combine variables in this way in your model if you think that the effects of one predictor are enhanced or diminished with varying values for the other predictor. In R, when you use formula notation for your model, using the star symbol for your predictors will build the model structure shown above. It will estimate the coefficients for x1, x2, and the product of x1 and x2. If you only want the product of the two, then use the colon symbol between them. The plot on the right shows an interaction. The plot here is x1 versus y, and each line is a varying value of x2, starting with small values on the bottom and high values of x2 on the top. The slope of the x1 versus y line increases as the values of x2 increase. This means, for the model structure on the left, the value of beta 3 is positive. Sometimes you want to encode categorical data into your model. This can be done using dummy variables, which are 1-0 representations of whether an observation belongs to a category or not. In order to avoid collinearity, you generally want to use C-1 variables, where C is the number of categories in the data. Otherwise, these three columns always add up to 1, which creates strong multicollinearity because the three columns are a linear combination. In the example shown here, the data shown are the first 15 rows of a data frame drawn from 3 states, California, Nevada, and Arizona. If the site is in California, then it has a 1 in the CA column and a 0 in the other two columns. The same goes for Nevada and Arizona. In this situation, if we wanted to identify the effects of these three categories, we would use C-1 equals 2 dummy variables with the implication that an observation with a 0 in both columns is in the third category. Imagine in this situation that California is our baseline and we want to see the effects of switching to Nevada or Arizona. We might use Nevada and Arizona as the dummy variable columns with the implication that a site with a 0 in both the NV and AZ columns is a site in California. If we set up a model to predict TD mean, which is the mean annual dew point, and we use these 4 other variables, the coefficient output in Excel data analysis is shown on the right. Here we can see that all 4 predictors are significant at alpha equals 0.05. Increasing annual precipitation and annual mean temperature increase mean dew point. However, for sites in Nevada, they on average have a dew point 3.4 degrees Celsius lower than the same precipitation and temperature in California, and in Arizona, this value is 6.8 degrees less. I'm going to editorialize here for just a second. Personally, I don't like automated variable selection techniques like stepwise or best subsets regression. I think that the risk for building a model that's hard to explain is pretty high, and that spurious relationships sneak in. When you start with a large number of variables and automate the selection of some set of those in a way that it maximizes an objective, like finding the maximum adjusted R-squared among combinations of predictors that are coming from a big pile, it doesn't feel very scientific. The predictors you test and evaluate should prove or disprove some hypothesis about the relationship between the variables. I feel like I should have a hypothesis that says that variables A and B together explain the variability in the response if I include both variables A and B in my model. If you have a large number of variables that you've gathered and they can all plausibly and possibly physically explain the response variable, then sometimes automated variable selection can be helpful, but I personally would rather stick to well-planned models that are simpler when it's possible to do that. In this video, we discussed additional considerations for multiple linear regression models. 2 key points to take away from this video are: the additional model complexity introduced in multiple linear regression requires checking for multicollinearity in addition to the 4 regular assumptions made in simple linear regression, and multiple linear regression opens up the types and forms of predictors that you're able to include in your linear model. Thanks, and come back soon to learn about other topics in our statistical methods in hydrology course.